We've got some fresh images of 3I Atlas, a third ever interstellar object observed from Earth, currently racing through our solar system.
3I Atlas is actually some type of alien technology.
The mysteries of the cosmos stretch beyond imagination, an ocean of shadows and phenomena awaiting discovery. From time to time, a rare, enigmatic visitor races toward our solar system, disrupting that silence and demanding attention. On the quiet nighttime slopes of Chile, a NASA-operated observatory known as ATLAS quietly scanned the heavens. In the early hours of July 1st, 2025, it detected a subtle disruption in the tapestry of stars, a transient speck streaking against the galactic background. At first glance, it seemed like just another comet, perhaps an unremarkable piece of rubble left over from the birth of some forgotten world. But as the data accumulated and astronomers scrutinized the observations, it became apparent this object was uniquely significant. This new arrival would soon be named 3I/ATLAS, with the I denoting its interstellar origin, an official acknowledgement that this was no mere debris from our own solar system. With its detection, 3I/ATLAS became only the third interstellar object ever confirmed in our system, a truly exceptional event in the catalogue of astronomical discovery. Astronomers for generations have speculated about such interstellar trespassers, but until Oumuamua streaked through in 2017, followed by Borisov in 2019, there had been only theories and speculation. To have a third instance so soon was both exhilarating and sobering. It raised a pointed question: what forces, random or regular, send these bodies careening across interstellar space and into our cosmic neighborhood? For the scientific community and the wider public alike, the detection of 3I/ATLAS was a source of both wonder and curiosity. Did this object represent more than just an icy relic or rocky survivor of some ancient planetary system? Was there something fundamentally new to learn from its sheer speed, trajectory, or chemical makeup? Each of these interstellar objects, Oumuamua, Borisov, and now 3I/ATLAS, offers a different clue about conditions and events beyond our solar system, and together they challenge pre-existing assumptions about what can cross between the stars. As news of the discovery spread, anticipation built rapidly. Scientists prepared to mobilize precious telescope resources for a rare chance to study an object not born under the sun's influence. The world watched as specialists began piecing together its story. Meanwhile, astronomer DeGrasse Tyson, known for interpreting cosmic phenomena for both professionals and the public, weighed in on the implications, emphasizing the necessity of careful observation and analysis above all else. The attention was well earned. For 3I/ATLAS, it quickly became clear, was a visitor with distinctive properties, namely an unprecedented velocity, well above what is typical for either native or interstellar bodies observed to date. Faster and stranger, the approach of 3I/ATLAS. To appreciate why 3I/ATLAS drew such attention, one must understand the context of celestial speeds. Most comets and asteroids tracing loops around the Sun travel at tens of thousands of kilometers per hour, terrifying rates by earthly standards, yet leisurely compared to what 3I/ATLAS displayed. Atlas's initial readings indicated a phenomenal speed, about 221,000 kilometers per hour as it plunged through the solar system. For comparison, Oumuamua, whose 2017 passage marked an epoch in planetary science, was observed traversing the Sun's realm at about 26 kilometers per second, or roughly 94,000 kilometers per hour. Even at that pace, Oumuamua was considered a record setter. But 3I/ATLAS moved outwardly faster, nearly 60 kilometers per second, or around 130,000 miles per hour. In the space environment, where distances are so vast and collisions so rarefied, differences of tens of thousands of kilometers per hour are highly significant. This extraordinary speed isn't simply an abstract statistic. Velocity in space is deeply tied to an object's origins and fate. A velocity of this magnitude relative to our Sun means the object is on a hyperbolic path. This is not a closed loop, but an open curve, confirming that 3I/ATLAS is just passing through, an interloper bound to make one sweep around the Sun before returning forever to interstellar space. But what could propel an object to such velocity? Most comets seen near Earth arise from the Sun's Oort cloud or Kuiper belt. Their speeds are dictated by their initial orbits and the Sun's gravity. Interstellar objects, unbound by our star, bear the imprints of the dynamics that ejected them from their home systems, whether through planetary encounters, gravitational nudges from passing stars, or the distant tremors of galactic forces. The hyperbolic excess velocity of an object like 3I/ATLAS tells astronomers that not only did this object come from outside our solar system, but its journey here likely involved interactions or events with staggering energies, multiple star systems, collapsing clouds, or perhaps the tidal push from the galactic center itself. While the velocity could simply be a product of rare circumstances, it is a true outlier, even among outliers. The question for scientists is not just how such a speed could be achieved, but what else it hints at. About the dynamics of other stellar systems, about the types of material and objects that roam the galaxy, and about the possible frequency of such visitors. The need to study such a rare, fast interstellar object is clear. Trajectory analysis confirmed the object would never come close enough to Earth to pose a physical threat. Its minimum distance would be about 1.8 astronomical units, nearly twice the distance from Earth to the Sun, removing any possibility of collision. The danger, as discussed by experts, is not physical, but scientific. The risk of missing vital information about objects, and by extension, processes that our models have not yet fully captured or predicted. Before we continue, don't forget to subscribe to the channel so you never miss updates on interstellar visitors like 3I/ATLAS, the mysteries they bring with them, and what they reveal about the galaxy we call home. Beyond a simple comet, puzzling properties. Once word of 3I/ATLAS spread, telescopes across Earth and in orbit were immediately tasked with observation. Spectrum analysis, light curves, and trajectory refinement became the urgent focus of a worldwide concerted effort. Studying faint, rapidly moving interstellar objects presents immense technical challenges, not least because of their velocity and fleeting proximity. One of the first questions addressed by researchers was whether 3I/ATLAS was a comet in the usual sense, a body consisting mostly of ices, outgassing dramatically when heated by solar energy. Astronomers closely monitored it for signs of coma or tail formation, as seen with Oumuamua to a small degree, and the far more overt Borisov. However, 3I/ATLAS revealed frustratingly ambiguous results. Early observations suggested some hints of volatile substances, perhaps water, but any such emissions were faint, inconsistent, and difficult to interpret given the object's distance and speed. A preliminary NASA assessment noted that the characteristics of 3I/A TLAS, while suggestive of cometary ancestry, deviate from conventional models. Its brightness, spectral signals, and lack of clearly defined outgassing led researchers to urge further vigilance and additional investigation rather than firm conclusions. Neil deGrasse Tyson, reflecting the cautious tone of the scientific community, remarked that, "For an object this substantial, moving at this speed, we have to consider all options, including highly unusual ones." His comments underscored not suspicion or fear, but readiness to follow the evidence wherever it may lead, and an openness to new mechanisms yet unconsidered. In the broader astronomical conversation, some researchers have noted that such velocities suggest powerful ejection events, such as the chaos of multiple star systems or the aftermath of collisions or disruptions in distant planetary architectures. Others compared the uncertainty surrounding 3I/A TLAS's physical properties to the uncertainties that surrounded Oumuamua, an equally enigmatic visitor with a light curve and shape that defied easy categorization. No consensus has emerged beyond the key fact. 3I/ATLAS is an exception among exceptions. Its presence is forcing a reconsideration of what is possible in the mechanics of planetary systems and interstellar trajectories. Reassessing interstellar risks. For the scientific community, the arrival of interstellar objects is not cause for alarm in the Hollywood sense, but a compelling reminder of gaps in our observational and conceptual frameworks. The physical risk of a collision with Earth was, from the start, ruled out. 3I/ATLAS would pass at a completely safe distance. However, its speed and unpredictability have highlighted a conceptual risk. The risk that our current surveillance capabilities and theoretical frameworks may be unable to promptly detect or characterize such events in the future, especially if such objects are more common than once thought. This concern motivates astronomers and planetary defense experts to advocate for enhanced sky surveys, faster data analysis, and more coordinated global communication. In discussions with media, the phrase "possibly hostile" has sometimes appeared, taken less as a literal threat and more as an articulation of the unknown aspects of such discoveries. No credible scientist has suggested the object is artificial or engineered with ill intent. Instead, the focus is on understanding natural events and ensuring preparedness for the unexpected. Astronomers regard 3I/ATLAS as a vital shot across the bow, not a danger in itself, but a warning that our models and monitoring systems must improve to account for rarer, faster, or otherwise unanticipated cosmic arrivals. Eyes on the sky, racing for data. With 3I/ATLAS on a hyperbolic escape trajectory, astronomers everywhere scrambled to coordinate rapid observations. Major ground-based observatories, space telescopes, and even amateur astronomers contributed data, striving to build a continuous record of the object's position, motion, brightness, and evolving spectrum. A key challenge was the sheer speed and distance of 3I/ATLAS. The object traveled quickly across the background of stars, requiring swift adjustments by those tracking it. Every day, the precision available for measurements and potential discoveries diminished, a race not against a threat, but against the inexorable clockwork of celestial motion. The prospect of sending a spacecraft out to intercept this object, much like scientists and engineers had dreamed of doing with Oumuamua was recognized immediately as impractical. Our current propulsion technologies could not reach, let alone pace, an object moving at such a velocity before it departed forever. Instead, the focus concentrated on maximizing the information gathered from Earth and near-Earth assets. This urgent international data collection effort marks one of the most coordinated responses to an interstellar object in history, echoing lessons learned from the missed opportunities during Oumuamua's brief passage. Each new observation of brightness, color, spectrum, or any sign of activity adds a layer of understanding and a test of our readiness as a planet to study the unknown. The evidence mounts, puzzles, and possibilities. As more data poured in, a tentative picture of 3I/ATLAS began to emerge, one marked by confounding traits rather than clarity. The high speed, ambiguous signatures of volatiles, and the difficulty in pinning down a clear composition or structure all serve as reminders of the difficulty of these studies. Models developed for comets, asteroids, and ice rock hybrids were successively tested and found inadequate in fully explaining the data collected on 3I/ATLAS. Some astronomers posited that only the most powerful of stellar events could impart such velocity. The notion of myriad interacting events, gravitational ejections, and perhaps the coincidental alignment of multiple bodies was entertained as a plausible mechanism. Still, the journey from hypothesis to confirmation remains long and fraught with uncertainty. While early speculation about non-natural origins, such as artificial propulsion or technology, was noted in some media, the scientific consensus remains firmly grounded. Extraordinary claims require extraordinary evidence, and all data so far point to a natural, if unusual, origin associated with the complex gravitational interplay in star systems. Instead, the focus for astronomers and planetary scientists is on collecting as much information as possible so that subsequent objects might be anticipated, identified, and perhaps understood with greater certainty. Open questions and the expanding frontier. The detection of 3I/ATLAS has prompted a wave of introspection and recalibration within the astronomical community. How many interstellar objects like this have visited in the eons before we had the capacity to notice? Are such objects common in the galaxy, or are we witnessing an unusually clustered set of events by coincidence? What does their composition tell us about the diversity of materials and events across star systems? The frequency of interstellar discoveries, once thought vanishingly rare, is now under renewed scrutiny. 3 in under a decade demand careful statistical analysis to discern whether our region of space, improved technology, or some heretofore unknown process is at work. Because many of these visitors appear unpredictably, momentum is building to improve detection. Through more frequent surveys, better automated data analysis, and perhaps even the early development of intercept missions able to launch on short notice. The challenge is as much about engineering and observation as it is about theoretical curiosity. Implications for planetary science and preparedness. Irrespective of any speculative risks, 3I/ATLAS's journey is already reshaping planetary science. The existence of multiple confirmed interstellar objects affirms that matter does indeed traverse the vast reaches between stars, and that our local system is not isolated. This insight alone dramatically expands the scope of planetary science, astrochemistry, and the search for the origins of complex compounds across the cosmos. For those tasked with planetary defense, protecting Earth by cataloging and modeling potential hazards, the case of 3I/ATLAS is a wake-up call. Survey strategies must now include anticipation of high-velocity, unbound bodies and not restrict themselves to the familiar patterns of native asteroids and comets. Flexibility, speed, and technological innovation are the new watchwords for those who monitor the sky. Likewise, those advocating for robotic exploration and sample return missions are now forced to reckon with the limits of current propulsion and reconnaissance technologies. The next interstellar visitor may well offer enough warning and opportunity for more direct study if lessons learned from current efforts are applied wisely. While the universe's fundamental processes are overwhelmingly natural, the persistent ambiguity of these visitors continues to stoke imagination among scientists and the general public alike. The lure of the unknown remains powerful, and researchers like DeGrasse Tyson urge an approach that combines wonder, patience, and skepticism. In each unexpected observation, there lies an opportunity not only to rewrite textbooks, but to expand the very sense of what is knowable. As 3I/ATLAS retreats back toward the depths of interstellar space, astronomers are left with both more data and more questions. No radio signatures, no technological indicators, no obvious evidence of artificiality have emerged. Yet the presence of material from other star systems within reach of our detectors is in itself a profound testament to the interconnectedness of the galaxy and the unfinished narrative of cosmic evolution. Our place in a dynamic galaxy. What 3I/ATLAS ultimately teaches is humility. We are only at the very beginning of understanding the full variety of bodies and events that populate the galaxy. For all the leaps in detection and theory, each new discovery brings a realization of untapped possibilities and processes. Looking ahead, planetary scientists and astronomers will continue refining their methods, expanding their lists of priorities, and jointly building a more complete map of our local slice of the Milky Way. In this effort, public interest and the calm, clear interpretations of scientists like DeGrasse Tyson play a crucial role. The scientific journey is powered as much by the drive to explain anomalies as by any set of comforting, established facts. As 3I/ATLAS arcs away from us, it reminds humanity of the importance of readiness, collaboration, and open inquiry. The universe remains implacably mysterious, offering no guarantees of simplicity or safety, but always rewarding the persistent search for understanding. As 3I/ATLAS vanishes back into the infinite night, it leaves us with a deepened curiosity and the awareness that the cosmos always has more to teach. As we strengthen our tools and sharpen our questions, let us remain eager and vigilant. The age of interstellar discovery is still in its infancy, and each new arrival holds the promise of fresh insight. Stay curious, keep searching the sky, and remember, the next messenger from the stars may already be en route, bearing secrets we have yet even to imagine.